start? Okay, it's always a pleasure to have Dmitri Khveshchenko here at the Institute. Just reminding you that Dmitri received his PhD from Landau Institute, and he did some postdocs at Princeton University and at Chicago, University of Chicago, and was for some time was an assistant professor at Nordita when Nordita was at Copenhagen. And since beginning of the millennium, he is permanently at North Carolina, Chapel Hill. So Dmitri is particularly known for his background is condensed matter, I suppose, but he's particularly known for his critical approach to attempts to apply holography ADS-CFT correspondence to condensed matter systems. So he will give a review of this today. Thank you.
Thank you for the introduction. I hope I'll have some positive things to say as well, not just criticism per se. As always, it's a pleasure to be here to experience yet another visit to IAPU, which is a great place with ever-increasing visibility and serving so well the community, both in South America and worldwide. So the story I'm going to present today has something to do with the approach to the so-called holography in general, but more specifically to its variants that have been discussed in the context of condensed matter physics. So to that effect, I'm going to first briefly review the so-called holographic principle as a general concept. Then we'll talk about its various generalizations that have been pursued in the context of condensed matter physics. Then as an alternative of what holography should be all about and the actual definition of it, I'll delve into the distinction between these two slogans, so to speak, where the former one was put out by Leonard Susskind and the other one by myself. That will be supported by a number of results and observations in the context of three specific examples of such duality, which will all point towards that latter definition of what we should be really meaning by holography. And close to the end, I'll try to come up with a proposal of what a tangible theoretical framework for formulating the holographic ideas might indeed be. In fact, in that context, we would probably never use the word holography, but rather refer to it as the somewhat modified, modernized, but more or less familiar hydrodynamics. Okay, and most of these observations were published in those papers over the years. So how it all came about? Well, the story started back in the early 70s, when it was first pointed out that thermodynamics of black holes requires one to think of those as the objects with rather peculiar property. Specifically, the entropy attributed to a black hole of a certain size wouldn't be a function of its volume, but rather its surface area, as if all the relevant degrees of freedom pertinent to the system were residing on a surface rather than occupying the bulk. And that, of course, was a bizarre suggestion to begin with, but apparently the only consistent conclusion that would be made out of the existing thermodynamic picture of black hole physics. It didn't take long for this idea to proliferate into, well, the theory of everything, so that there were early proposals of thinking of the entire universe in this holographic sense. Examples here represent the various holographic universes in different dimensions, starting with the somewhat peculiar case of zero spatial dimension. And by the way, throughout this presentation, the small d will stand for the number of the spatial dimensions only. So time will be separate, and anything on top of that will add to the overall count as well. But if it's a spaceless case, which is rather special, an example of what a holographic world would look like is represented here by the Escher's tessellation kind of picture, which gets more and more complex as one approaches the boundary from inside. And it's actually remarkable how ingenious that early view, which of course had nothing to do with the later holographic ideas, turns out to be. This picture is used throughout all the texts nowadays. If the number of spatial dimensions is 1, the proper picture of the universe is somewhat similar to a cylinder. If it's greater than 1, including the case of physical relevance, well, then it's more or less unimaginable, with some radially changing metric, which will appear later in a number of formulas, and an analog of a black hole sitting in the middle, which is required to put things in thermal equilibrium, so to speak. So these are different examples of what is nowadays referred to as the anti-de Sitter geometry of different dimensions, the definition of which is that they solve the Einstein equation with a constant negative curvature, as opposed to a positive curvature, which would correspond to the so-called de Sitter space, which is, one might argue, or is the only physically relevant one when it comes to cosmology. But at the level of mathematical constructs, which are not about the real universe, but what we think of it, the anti-de Sitter case seems to be more prevalent and more appropriate to what I'm actually going to discuss. The first such example was due to Maldacena around 1998, and then his followers that came up with a slightly different versions of it a bit later. And it's all referred to the correspondence between that ADS gravitational type of theory versus what's called here conformal field theory. And again, that first example would be establishing as a conjecture, of course, would be establishing correspondence between the rather peculiar maximally supersymmetric gauge, or Young-Mills theory, living on the three-dimensional boundary, on a brane, as they would say, over a four-dimensional, it's equal for supergravity, or rather in its dimensional reduction, which is itself a dimensional reduction of some type of a superstring theory. And in short, it would imply that this specific type of a gauge theory, which is kind of distant cousin of QCD, but not quite. Unlike QCD, there is no confinement here, nor asymptotic freedom. The coupling strength does not run as a function of the scale. Things are frozen in the theory, but it's conformal. Okay. And of course, being maximally supersymmetric and also a priori Lorentzian scale invariant makes it a special example, but one would argue one can still learn something about a specific regime which would also occur in the physically relevant QCD theory. And yet, the interesting property of that conjectured correspondence would require a certain condition to be met. Specifically, the rank of that gauge group N would better be large for the duality work in such a way that while the theory on the boundary would be this strongly coupled gauge field theory, the one in the bulk, supposedly dual to it, would turn out to be instead weakly coupled, and therefore ideally would allow for some classical or semi-classical treatment as opposed to the genuine full-fledged quantum analysis as one would normally think of of the only way to describe that strongly interacting gauge field theory. In other words, instead of attempting the impossible task of computing those multiple Feynman diagrams, one would choose to solve essentially the classical equations of motion of what appears to be some modified gravity plus Maxwell type of action for some vector fields, plus perhaps some scalars added to the mix. And of course, conceptually, that would, while still technically challenging, that would be an easier task to carry out classical calculations instead of impossible diagrammatics. Now, that was all conjectured and discussed in the context of, well, high-energy physics, string theory. But it didn't take long for these ideas to start permeating other fields. Next thing you notice, there were already discussions not only with regard to the strings, but gravity itself, quantum information, and it was only a matter of time for the condensed matter physics to be pretending to fall into the same holographic type of a framework. And of course, from the beginning, there were all sorts of reasons to doubt that this could indeed be possible. Well, because clearly in condensed matter, we never have that supersymmetry, let alone maximal one. The systems you discuss are neither Lorentz, no scale, apart from the special points known as phase transitions. They're not even translationally invariant, because usually it's a lattice kind of ionic system with electrons added to it. Not even rotationally invariant. Also, physically, we would only have a couple of those components. So the n, which would better be large, is hardly ever greater than 2, spin up, spin down, so to speak, although it could also be amplified by, say, number of so-called valleys and stuff. But it is still a further 1, never gets big. And when it comes to the boundary theory and evaluation of the strength of interaction in it, it's never really in the regime of, unless it's a problem in the graduate level condensed matter theory textbook, the coupling strength is neither strong nor small. Crystals tend to form when the kinetic energy balances out the potential one. So we're always find ourselves in the intermediate regime, which incidentally is the hardest one to handle, okay, where the coupling is of intermediate strength. Although artificially one can create and discuss situations where the, say, charge carriers would be anomalously heavy, flat band kind of situation. But usually it takes a synthesis of some artificial systems as opposed to naturally occurring ones. On the other hand, an optimist would argue that, well, there's a certain deal of universality observed in various systems at strong coupling, which I will elaborate on later. There are the signatures of some sort of common hydrodynamics, which may be indicative of some sort of gravity to fluid duality. Again, there will be more on this close to the end. Many of these systems, experimental systems, seem to demonstrate a certain universality in terms of the, well, somewhat mysterious Planckian, as it was coined, dissipation, that is, whatever is the typical rate of thermalization, which, by the way, is a hard thing to define, depends on the definition, pretty much always, when measured or extracted from the data, turns out to be of whatever temperature, just T to the first. And that's also perhaps suggestive of something. So all those things considered, people around the year 2007 came up with, they wouldn't formulate it like this, but that's what, in effect, their later activity would suggest, that a decision was made to come up with a scheme which, with a little bit of exaggeration, sounds like this. Whatever theory you have on the boundary, and interesting means, well, interacting, perhaps strongly interacting, At weak or strong coupling would or should be dual to some kind of a gravity, which you can pretty much choose at your will based on the previous experience, availability of numerical packages for the analysis of that theory, availability of similar works on the topic, because as I will show, that's how these people operated. It wasn't a single kind of singular proposal. That was a consistent approach to things. So as a typical example of one of, say, recent papers, here you see an action chosen to describe that classical generalized gravity, and it's a sort of common Einstein / Maxwell / dilaton type of action. Here is a typical rotationally symmetric metric, which they would use, again, just out of the blue. The motivation attached to it would sound pretty much like this. Well, literally, DSMT corresponds as string theory-based framework that emerges as a promising, they say, tool for studying circulated constraint systems. A paragraph later, it would sound like correspondence is a natural tool. All right? Just a mild example of how people would motivate themselves and their readers. Okay, I will show some more later. That whole approach boils down to the following scheme, which certainly had its appeal and its advantage of being always capable of producing the result. No matter what, you are guaranteed to obtain the result. Whether or not it has anything to do with reality is a separate issue, which I will also get to. So the approach goes like this. It's a so-called bottom-up one. Choose your favorite theory of classical gravity plus electromagnetism plus other fields. You saw an example of it. Choose your favorite black hole type of solution of the classical equations of motion, based again on your experience, availability of numerical tools to address it, and stuff like that. Okay. Borrow, literally, for the lack of an alternative, the so-called from the so-called holographic dictionary, borrow the formulas which would supposedly identify the physical observables such as current, charge, thermal current, etc., in terms of those gravitational and other fields in the bulk. Look around, you'll probably find some experimental data which are reminiscent of the numerical plots obtained with the use of those metrics. Well, claim to have these results explained, well, then probably have some hard time publishing PhysRev B. But not in the Journal of High Energy Physics, where all that stuff ended up published. All right. The early claims of the grand successes of this approach were numerous. And in fact, it looked as though literally for nothing, cheaply, one would obtain, one would gain control over a whole bunch of different situations which had resisted any attempts to be understood prior to that. You see how nicely that optical conductivity as a function of frequency matches the experiment. You see this remarkable agreement between the supposedly exact Monte Carlo results in a certain lattice system with the holographic prediction. They were capable of explaining the entire complex phase diagram of, say, ITC cuprates. They would claim not just qualitative but quantitative agreement in terms of the actual coefficient of certain relations established experimentally. They would claim remarkable similarity with affinity with the results obtained in vastly different advantages, one of the QCD type, the other called atoms, in terms of the, for some reason important for this business, ratio between the so-called shear viscosity and entropy density. And so it started to look overwhelming at some point, until it turned out that under closer scrutiny, neither some of the results can be reproduced, nor could one trust the most impressive points at slow frequencies, or given a large number of parameters, one can sort of make things look like the real ones. While one relationship was reproduced with the parameters they chosen, the other ones, also empirical experimental results, wouldn't be reproducible. The way of extracting that ratio from the experiment turned out to be completely not wrong, but opposite of what everybody else would do in that business. Okay, and again, there was no mentioning of any attempt to repeat this experiment. That is to say that there might have been some anthropic factor involved. Huh? Unconfirmed, yeah, because apparently there were later attempts to obtain that particular dependence, okay, which were unsuccessful, and the authors reluctantly reported that we cannot obtain the same asymptotic. But I would, be concerned with things like this, because a theory which operates way outside of its applicability regime, at least it requires large n, which is equal to 1 in this particular case, right? When it claims a quantitative agreement with experiment, I think it's, this theory gets much more explained and to do than just the data. Right? Shouldn't be like this, or else it's a fluke, fortunate fluke. Anyway, those were sort of early data. One might wonder as to whether things changed in the meantime. Well, 10 years later, we still look at the optimistic, upbeat reports which make specific, that's important, specific experimental suggestions. But they're also ready to admit that, unfortunately, the experimentalists working probably next door failed to find confirmation to those predictions. In fact, you must give them a credit for confidence when they say the apparent contradiction certainly challenges the experimentalists to either discover the experimental conditions to observe the predicted plasmon mode, or come up with arguments to explain why it cannot be measured. As they used to joke at the old Data Landau Institute, when experiment does not confirm theory, it's only worse for the experiment. It's, like I said, yeah, these people are confident. Anyway, so what's the current status of this whole activity? As a rough estimate, but if you just go in the archive and try to count the number of papers in the condensed matter category or cross-listed with high energy, the number is quite staggering. Yeah, quite a few. Books have been published on the topic. Okay, so it was as though the Phil Anderson's slogan were tested once again. If you repeat it sufficiently many times, does it make it true? Like different, right, from a single isolated claim. Unfortunately, as far as I can tell, most of these studies would shy away from trying to pose and hopefully answer in some form the central question: why holography? What physical mechanism, what physical nature can it possibly have? What is behind the holographic conjecture? Well, Phil Anderson was actually the first one who came up with his own critique of that approach back in 2013. And then it was followed by some isolated voices of the lone dissenter. And actually, I must say that, trying to swim upstream was not a pleasant journey. You feel like a heretic in the world of faithful followers. And they treat you as such. But just in sheer numbers, well, the field has gone under the radar for the past couple of years, and I sort of waited for it to come back, which it didn't. And it stays at that low level. And the question now is, what was it? A genuine theoretical breakthrough, which we should be trying to rethink and improve, or it was an example of what, in his famous speech at Caltech, Richard Feynman called cargo cult science, referring apparently to the story of this indigenous tribe somewhere in the South Pacific, the members of that tribe were observing cargo planes flying overhead. And they wanted one to land, so they built their own, which looked very much like the real thing, from twigs and stones. The only difference was that, of course, was unable to fly, but it looked cargo cult. Hence, so specifically, the question one might be interested in asking is, could any of those claims still be right? Well, possibly for their own reason, which again is quoting from Phil Anderson. All right? And that's my take on it. Especially nowadays that the low-hanging fruit, so to speak, has been all collected and largely turned out to be rotten. I think it's a good opportunity to start rethinking it anew. What could one say about the possible physical origin of holography? Well, indeed, one can imagine several sources of those extra dimensions. One would naturally occur in the context of what we would call realization group, where that extra dimension plays the role of energy or length scale or whatever that basically tells you how well you can resolve the different microscopic or macroscopic features. And that's where the RG as realization group versus GR slogan comes from. Okay. Then one can think of a certain construction which has become popular lately, known as tensor networks, which is, at least which originally was the way to construct a certain class of wave functions for interacting systems, but seems to have this built-in geometric feature of its own, and is indeed suggestive of something potentially holographic. We've also witnessed a number of occasions where some emergent geometry would naturally appear, be it in the context of phase transitions, which is probably the earliest emergence of that kind, Fisher-Ruppiner metric it's called. In quantum information theory, it's known as the Burris metric. In those numerous papers that you find nowadays in condensed matter context, it would be the quantum geometry of essentially the single particle Bloch bands. That's what quantum geometry is usually associated with, although the other version would be its emergence in terms of the time dependence of those single particle states. This, by the way, as an illustration of the remarkable similarity between that tessellation picture of the ADS2 and a tensor network, which again may be implying something important. Last but not least, we do have some purely geometric observables, some of which are physically quite important. For one, the Hall conductance is something which one routinely calculates by using the so-called Kubo formula. And if you never think of where that comes from, it might come to you as a surprise that at lowest temperatures, the dependence of that Hall conductance on the chemical potential, really, not the density, would follow the stepwise discrete kind of it would acquire this appearance, but the mystery gets resolved once you realize that what you're calculating at zero temperature is nothing but the topological first Chern class, and then it's got to be quantized for sure. Okay? Another quantity which has been under much discussion lately is the so-called entanglement entropy, which, unlike the Chern class, is not quantized as a continuous function, but it has been identified with a certain area with all the reservations and additional terms in the context of page curve and stuff, which I don't want to go into. In the sort of simple cases, it turns out to be equal, where it can be tested independently, to the area of some extremal surface going inside into the bulk. Somewhat disappointingly, the list of those geometrized observables is rather short. And I think holographists would be better off spending their time and resources on extending that list by adding more quantities of interest with potentially geometric origin or nature to that list. However, it's not the only kind of observable we deal with. So even if the sigma xy, the Hall conductivity, can be interpreted this way, its longitudinal counterpart does not seem to have any apparent geometric nature, and therefore whether or not it will be amenable to some sort of holographic analysis is not at all clear. Huh? Well, the Hall conductance is sigma xy. That's the same thing. These are, general arguments. This particular one is about the possibly geometric intrinsic nature of such quantity. Right? If it allows for a representation in terms of the Chern class and it's quantized, it clearly manifests its geometric nature. And then perhaps, hopefully, perhaps it can be put into the context of some geometrized theory, which we may or may not call holography, depending on preferences. That's why right. That's why I would like to see that list continuing further down. But since this talk is on condensed matter applications, those would rather be not Wilson loops, but say conductivities, or more generally thermodynamic and kinetic coefficients, which is what is experimentally measurable. Right, and we don't seem to have many such examples. Now, what's the difference between holography as originally envisioned, I wouldn't say defined, but envisioned, and its sort of simpler analog, the conciliation price, if you wish, that is proposed under the whimsical name of holography. So holography, I would define as a kind of correspondence between two systems which clearly have different dimensions. Whether the difference is 1 or 2 or more, it's up for a discussion, but they live in different dimensions, period. And the physical mechanism for such a correspondence would be unclear at best, or non-existent. Right? Now, what I call holography would be a duality between two systems which seem to have different dimensions, but in fact live in the same one, although it may not be immediately obvious or even after some analysis. Right? But eventually, one should be able to figure out that both are different representations of the same thing, only potentially looking very different, to the extent that one looks like gravity in the bulk and the other one is some sort of many-body quantum theory on the surface of that bulk. We have some examples where systems would have the topological nature of the theory operating in the bulk, so that all the important physics, all the degrees of freedom, actually happen to be confined to the boundary. All right? And the difference between these two, in my view, is the difference between those slogans. That's what they basically, that's what meant to represent. Now, can we actually see examples of this? Well, that's why I want to present a few such examples, demonstrating that indeed all those instances where people would quickly claim to be holographic and therefore proving the case turn out to be of the latter, that is, Hall-o-graphy nature. All of them. So case number one is the famous SYK model, which was also discussed at length at the recent conference here by a number of speakers. Originally, it was put forward in the context of spin glasses, as you know, then was claimed to be a sure example of low-dimensional holography. When you press people into mentioning at least one example where holography was established for sure, they always say SYK. Now let's see how this works. So it's, of course, a theory of some fermions which interact as a cluster. So in reality, it's a quantum dot kind of system or complex nucleus. By the way, the history of that model goes back quite a few years as compared to the Sajidov Yi's application of it when it was first conceived in the context of complex nuclei. Moreover, the randomness of the amplitudes of these interactions does not seem to be crucial. And when they say, well, this holographic example requires an ensemble of systems, well, not quite true. There are completely non-random models with exactly the same type of behavior. So what, in fact, is central here is the emergence of a certain effective description, which it can be discussed in detail, and we can go one line after another, matching these results obtained in the SYK theory itself, as opposed to those delivered by the two-dimensional gravity, which would be its dual analog. But the central property behind that mass is a certain symmetry, here applied to the two-point gain function, the propagator of those fermions. And the physics which it describes is the theory of deformations of a closed curve, which one might think of as the boundary of that ADS2 universe, which appeared a couple of times already in the form of the Escher's graphics. Now, curiously enough, as far as the mass is concerned, the solution of that sort of equation mimics the one for the bosonic counterpart of this equation obtained in the theory of phase transitions by Ptashinsky and Pokrovsky years prior to that. Now, this solution demonstrated interesting and seemingly unphysical properties, such as the entropy that wouldn't disappear at zero temperature, which was later interpreted in a certain way as the result of having the non-commutativity of the two limits, n to infinity and temperature to zero, and the accumulation of the states at the lower bound of the spectrum. It would demonstrate some maximal, actually, chaos in terms, when measured or detected in terms of a certain type of correlation function. But again, central to all these properties was the symmetry, the conformal symmetry, and therefore the effective action resulting from its spontaneous violation. But later, and again, I'm not sure how much others would agree with that. Later, it was demonstrated that one can achieve a similar description, differing in details but very similar in spirit, by generalizing that SYK model to the extent that it would be a sum of the different SYK Hamiltonians with different number of interacting fermions. Okay, so Q originally would be, say, 4. and it's even. In general, the Q equal 2 case would be somewhat trivial, corresponding to what one might call a Fermi liquid in the spaceless universe. But when there's a collection of such terms, they all interfere and compete with one another, and one might wonder what would happen in such a complex case as well. What turns out to happen is that at the end of the day, for all these models, one arrives at a certain description, which here is the one corresponding to the original SYK, and it looks like what they would call a Liouville action for a certain scalar bosonic field phi. But the truth of the matter is that even if we combine the different Qs here, different terms in the Hamiltonian, the only thing that changes at the end of the day is this potential. One might call it a potential, if this were to be viewed in the sense of quantum mechanics. Because so far it was like field theoretical, but one can then derive a quantum mechanical Schrödinger type of equation out of it. And then this exponential term becomes exponential potential, with phi playing the role of a coordinate in that one-dimensional quantum mechanical problem. So what changes when we combine those terms is the form of that potential. Okay, for instance, by adding together the Q equal 2 and Q equal 4 terms, we end up replacing the Liouville potential with a Morse one. Right? And then there are several other examples where certain more complex potentials emerge. But it's all of sort of the same kind, as it turns out. However, these are all, in physical manifestations, they would be all rather different. All right? Now, what makes them, what lands them in the same playground, so to speak, is the observation that all those Hamiltonians can be mapped onto the single particle Hamiltonian of a charge moving in a certain generally curved geometry in the presence of some generally non-uniform magnetic field. Right? So there's a Hamiltonian of a different, now two-dimensional particle, which you can think of as a non-relativistic charge, moving around in the presence of some vector potential, which too varies from one point to another, representing some position-dependent magnetic field. All right? Then one can discuss such things as the actual partition functions for these quantum mechanical problems, one being of the bulk, so to speak, that is 2D, and the other one being of the boundary, that is 1D types, and do Laplace transforms, obtain density of states, which people like to calculate in this business. And it turns out that all those pertinent gravity actions, be it of the type of generalized what's called JT or Jekiev-Teitelbaum, or Harari-Lifshitz type, when the spectrum has anomalous dimension itself, they all boil down to the description that one can match with that generalized Hamiltonian of a particle in magnetic field. So yeah, it took some observations to be made to that effect. What then the implication is that okay, I should probably go back a little. Is that on the one hand we would have these potentially complex two-dimensional gravities, okay? And naively, in each of them, a description in terms of the phase space would involve two coordinates and two conjugate momenta. Okay? But just like in the problem of a particle magnetic field, when it's sufficiently strong, which also ostensibly has two coordinates on a plane and two momenta, there is only one pair, one coordinate and one momentum, which are physical and correspond to the dynamic degrees of freedom. The other pair is frozen out. You can think of this as the physics of the lowest Landau level, or any Landau level, when the separation between them is large. Okay? You can disturb the electrons at that partially occupied Landau level, and they will stay at it. They will change their quantum states, but remaining within the same Landau level freezes out half of the degrees of freedom. Okay? It looks two-dimensional, but in fact it is one-dimensional. Hall-o-graphy. Another example of what happens in one higher dimension, which has been studied to some extent, to the lesser extent, but nowadays I guess they're catching up, and there are more papers appearing on the ADS3 versus whatever is the two-dimensional boundary theory. And here one can recall that, in fact, what we're talking about in terms of the one-dimensional boundary is one of those numerous one-dimensional theories which can be described in a number of ways, but in particular in terms of the densities and velocities, or if those particles are fermions, in terms of their right and left Fermi momenta, so that the density of those one-dimensional particles and the velocity with which they move would be a simple linear combinations of those two, left and right Fermi momenta. And of course, if there's only one, we would call it a chiral theory. If all these fermions are moving one way, there's only one Fermi point and not the other. And they can be also multiplied if the corresponding Fermi surface has more crossing points, then the number of these modes will increase too, accordingly. But on the mathematical side, there is a rich geometrical structure involved here, known as W infinity algebra, and one can operate in terms of these purely geometric quantities to do certain calculations. But again, and here it's even sort of more transparent, we are in a situation where that one-dimensional physics now represents what happens in the bulk, right? And the bulk itself appears to allow for a certain description, which I will get into in a moment. While the boundary theory appears to be not unique, but it can be one out of many, whose Hamiltonians rather are in involution and form a certain class of what people would refer to as an integrable system. Okay? So with the properties of those Hamiltonians satisfied, the equations of motion would be rather simple in terms of those Hamiltonians and their functional derivatives. And the first member in that class is what we usually call Latinger liquid. That is a simple quadratic theory where the Hamiltonian is just quadratic in terms of those right and left Fermi momenta. It describes simple bosons propagating with the speed of light, so to speak. The spectrum is linear. They are nothing but density waves in this context. Okay? However, already the next term in that family, the second member of that Korteweg de Vries, as it should be called, family, is less trivial. Okay, and it looks like this, and it can too be either considered on its own or added to the first member of the family, in which case it would describe the physical one-dimensional fermions whose dispersion is not exactly linear, it's only approximation, but has nonlinear corrections to the spectrum, which these high-order terms would originate from. If one were to describe microscopically the one-dimensional non-relativistic fermions by going beyond the customary lowest order approximation. As an interesting surprise, in the strong coupling regime of the low momenta, it shows that excitations have completely different dispersion from the sound waves. Although asymptotically, there will be just a power, an integer power law at small momenta. These are more like soliton waves with this peculiar fractional dispersion. Now, what happens in the bulk, on the other hand, and it's ADS3 case, remember, would be described by the now three-dimensional integral of the Lagrangian density, which, once again, just as in the previous ADS2 case, appears to be totally topological. That is to say that there are no dynamical degrees of freedom in the bulk, no gravitational waves in the usual sense. All the physical degrees of freedom of that gravitational theory sit on the boundary, where they match that KdV type of potentially complex KdV type of dynamics. In terms of the formal description, one would use a representation, rather surprising representation of that gravity theory in terms of a pair of Chern-Simons theories, from which one can extract the metric itself as essentially a product of two vector potentials corresponding to those Chern-Simons fields, with the equation of motion being that of zero curvature. And that's the Einstein equation in these notations. Well, then in order to match with the KdV on the boundary, one has to choose those vector potentials in a certain way so that they would be endowed with a certain p dependence, which p can be thought of as a radial degree of freedom, the one which disappears when we proceed from the bulk to the surface, the boundary, and then the x and t will remain as the one-dimensional coordinate and time along that boundary. And this is how one can discuss the emergence of a whole number of different integrable models mentioned here. Yet another example, which is probably less known in general, and certainly not as extensively discussed as the previous two, is the problem of so-called resonant Fermi surface scattering, which was first brought about in the studies which tried the following. Imagine a system of many interacting fermions in an arbitrary number of dimensions, which, however, mostly scatter off of each other in the S-wave channel. Okay? And that the other scattering amplitudes are suppressed. Then this restriction to the scattering momenta being all L equals 0, S-wave, imply that the green functions can be expanded in a certain quasi-one-dimensional basis. Okay, basically you only follow the radial dependence, and the angle is already taken care of by projecting everything on the S-wave harmonic. And then that one-dimensional radial variable which goes in and out can also be unfolded into going from plus infinity to minus infinity through zero, and makes it chiral in this way. Okay. So after some manipulations, the pertinent Dyson-Schwinger equation can be cast in a supposedly one-dimensional form, and then solved as a one-dimensional problem. And remarkably, it turns out that the thus obtained green function in the real space of radial degree of radial coordinate versus time, or its Fourier transform in the omega k domain, they both show this peculiar behavior, which one would immediately identify as what we call spin-charge separation, in the absence of any spin, remarkably. Okay? When such things happen, when instead of a single pole, there is a branch cut of two factors, and the velocities, exponent velocities are different, that could be the case of spin and charge degrees of freedom separating from each other and propagating independently at different velocities. That's what gives rise to such type of dependence. Here it emerged in the absence of any spin, and therefore spin-charge separation is not even an issue. But pursuing this observation further, one could argue that it can as well be reproduced in terms of the three-dimensional motion, the geodesics, literally, within the ADS3 bulk, if the geometry is of the kind which one might call chiral ADS3. Okay. Now, I suppose the proponents of the holographic approach at this point would argue that here's another spectacular achievement of the holographic theory, because we once again match the physics in the bulk in terms of the propagator to something that can be computed independently on the surface. In my view, it just means that, once again, the theory in the bulk is topological, has no dynamics of its own, and it's not that surprising to be able to obtain the same formula both ways. That's what I'm saying. It looks like one, but it is not, because these fermions do not even carry any spins. If one adds spins to the picture, well, there might be an additional branching of that kind, but that will be, separate. It would routinely occur in the absence of any, I would say, selection rules, because what this calculation is based upon is a certain selection in terms of those angular momenta of the scattering particles, which makes it effectively one-dimensional. So spin charge separation, when it happens in 1D, is just immune to this property. It's not affected by any such selection rules at all. But it's another feature which looks holographic, but is not. Or may look to someone who is inclined to see it this way. I'm not. By the way, if anybody cares, as people seem to still care about the High-TC Coop rates, which in a normal state show that linear temperature-dependent resistivity, well, this theory has it too. Okay. In fact, interestingly, originally this kind of analysis was meant to show just that under certain conditions, like this restriction to the S-wave channel of scattering, the resistivity would invariably become linear, or conductivity would go at zero temperature, at frequency as 1 over T. Curiously, Sajdev and his disciples have produced, I believe by now, 4 or 5 different mechanisms which all indicate linear resistivity. And I wonder what they think in terms of prioritizing those. Like, when there are 5 explanations, it's a little too many. And they are significantly different. That is, they emerge from different calculations. Anyway, what this seems to suggest or indicate is that perhaps we should be really thinking of the possible holographic interpretation in terms of some sort of metric which would emerge out of the quantum states in question, out of those states themselves, right? And if we can come up with some sort of reasonable metric, well, perhaps the intervals and things would naturally emerge as functions of the coordinates, and perhaps momenta, because we would be operating in the phase as opposed to coordinate space, where there are x's, coordinates, and the conjugate momenta p, and they should all appear in that metric. It's then not that surprising to see some correspondence to these imaginary metrics invoked by the advocates of that orthodox holographic approach. Right? On the surface, one can make them even identical. And of course, the history of viewing quantum mechanics as some sort of hydrodynamics goes back to, well, the early days when there was first proposed to treat a wave function as a product of square root of density and some sort of phase, which is action. And in terms of those, the Schrödinger equation turns into what we know as the Navier-Stokes one. in practice, one would pursue this approach, which has been around for a number of years, where we will try to look at the phase space of a generic system as some sort of manifold where certain operations can be added. The so-called star product, the definition is here, the Moyal brackets, which would generalize the Poisson one, and therefore would allow the natural transfer from semi-classical to genuinely quantum regime and its description, where the action would naturally include this sort of analog of the Berry phase with the certain constraints added. And at the end of the day, the equations of motion would look like a systematic attempt, a systematic improvement of the classical Boltzmann equation, which would be the lowest order approximation in this equation. Then the next order would correct for, would bring out the first quantum correction and second, etc. And this approach, has gained some popularity lately, thanks to these vigorous young researchers, and it's even referred to as the Chicago approach to quantum condensed matter physics in general. Interestingly, this Fox forgot to mention before they were reminded that in the context of some exotic magnets, and then specifically in the context of interacting fermions in what at the time thought to be the theory of cuprates, this had a longer history. Curiously, this Fox reacted to the attempt to bring them up to this reference by saying in the modified version that the early applications of our theory appeared earlier. The early applications. Leaving the citation matters aside, what this approach allows one to do is to focus on the Wigner function as if it were not just a function, but a sort of field variable in some kind of imagined path integral, right? But of course, in terms of that variable itself, things are exact, but hopelessly intractable. One always needs some approximations. And the natural one is to switch from that function itself to its moments, which have a clear physical meaning, depending on that power of n, for example, we're talking density, momentum, energy density. In 1D, by the way, one would be better off keeping track of all of them because there are infinitely many conserved currents. And that is a somewhat separate story. But then doing these momentum integrals and reducing the function to its moments is in effect similar to doing dimensional reduction from what it is in the full-fledged phase space where there are d coordinates, d moment, and time, down to possibly as little as d+1 coordinates. For instance, as an example, in the frequently discussed case of two spatial dimensions, the resulting densities would carry the dependence on where you are in space, two-dimensional space, time dependence, and also the position on the one-dimensional Fermi surface. This would naturally arise in the context of those empirical bosonization schemes, where they would divide the Fermi surface onto so-called patches at different positions and try to account for the interaction between those different patches. The attempts which have long been, which raised some hopes around 95 or so, but later was realized that the curvature of the Fermi surface cannot be completely eliminated or neglected, and that changes all the significant asymptotic behaviors compared to what one finds naively. in the d equals 0 case of SYK, well, there is no integral at all. And the theory which I was presenting here, that generic, where is it? Generic theory, which in its original cryptic form looks like this, amounts literally to the diffeomorphism invariant Schwarzen action, as of course it should, because we're talking about the dynamics of an incompressible droplet, be it a phase space in the Liouville sense, or Hall, or droplet of electrons in the Hall effect. Same thing, where the space is actually coordinate rather than phase. This can be pursued further towards arbitrary high dimensions, where one would use certain metrics with the specific dependence on that extra momentum variable, and reducing to the moments, one arrives at, well, essentially hydrodynamics in terms of the local velocity, local temperature, local chemical potential. And my understanding is that this kind of approach even preceded the orthodox Hall-o-graphy as we know it. It goes back to the earlier days when people tried to establish the correspondence between those bulk gravities and some sort of imaginary fluid near the event horizon. Okay. In that regards, the sort of proper line of thinking, also by analogy with the low-dimensional cases, would be the duality established between that classical gravity and essentially classical fluid, which might have some internal structure, but those would be details. So that is where it is, this whole field it seems to be at the moment. But I'd like to recap that, first of all, when it's about the lowest dimension case, d equals 0, the physics of the SYK type can be, indeed identified as the behavior of the topological ADS2 type gravity. And literally, these are different representations of the same thing, which one might also call a particle in non-uniform magnetic field on a curved manifold. In one dimension higher, the similar kind of relationship between the ADS3, also topological, and the KDV and other integrable formulas on the boundary would again stem from the possibility of doing the same calculations by using different frameworks, which upon a closer scrutiny, turn out to be identical because half of the degrees of freedom, which seems to be present in the bulk, disappears, in fact, and then it matches the one describing the boundary. Now, a similar sort of reduction can be also observed in the context of generic systems, but perhaps the technically best way to see it is through that phase space representation and its reduction in terms of the moments of the Wigner distribution function, which naturally results in some sort of boundary hydrodynamics. And although all these points are up for discussion, one thing I'm pretty sure is that the orthodox approach that has been in use so far, before it ended, with this voluntaristic choice of the underlying theory and the metric, had its own value of basically exposing the problems with this approach. But the only, I think, fair way to describe it is to quote Wolfgang Pauli, who would probably call this kind of theory as not even wrong, meaning that it's impossible to assess its true status because it does not follow the accepted framework of calculations of thinking. And, and over time, of course. That's where I would stop. The story obviously continues, or at least I think it should continue. But there seems to be fewer people willing to do that nowadays, especially with the rise of artificial intelligence, big data, machine learning, and stuff. But the fundamental question remains. Either holography is a new law of nature, and then all the textbooks would have to be rewritten with the Newton's equations and Schrödinger equation being derivable from holography, or it's just an illusion, which simply means that the other system we're trying to establish correspondence with is described in a non-minimalistic way. It has redundancy in its description. But when minimized, will look and feel like the other one. Okay.